Hello and welcome to the latest session for our Opti system software. My name is Joshua Donald and I'm the Photonics Applications Engineer here at OptiWave, and I'll be assisting your host Ahmed Attia. The webinar today will focus on LiFi channel characteristics. We will have a Q&A period at the end of the hour-long presentation, so feel free to go ahead and use the questions panel and type in any questions you have there, and we will answer all the questions at the end of the presentation. Now, over in the handout section, you'll find the PDF that's used in the presentation. Feel free to download and use that at any time. And lastly, we'll be recording this webinar and emailing the link to everyone an hour after the presentation. So if you want to review the presentation, you can see it in that email. With that said, let's get the webinar underway. I would like to introduce your host, our Director of Optical Systems, Ahmed Attia.
Hello, everyone, and welcome to this webinar, which we will talk about LiFi channel characterization. And this webinar will include an introduction. Then we're going to talk about the theory for LiFi channel. And we're going to talk about the channel component, LiFi channel component in OptiSystem. We're going to talk about its features, about the parameters used in the component, and the possible results which you can achieve by using the calculation of this component. Then we're going to do a live demonstration. At the end, we open for question and answers. Okay, in this graph here, we show a block diagram of a possible indoor visible light communication system where you have a room, basically have a length, a width, and a height, and you have a possible one or more light sources here, which could be visible or invisible sources. These sources would be modulated and carry the information, which will be transmitted into the receiver sitting in this room. The ray geometry of a LiFi system is depicted in this figure here, where we have a light source here, which is an LED, and the receiver, which is a PD. The receiver has a field of view, which is described by this angle here. And the light emitting source will transmit the modulated signal basically into the receiver, which the rays can be received directly into the receiver using this kind of ray, for example, which we call it line of sight ray. And it could be reflected from any surface in the room, and the reflection could be single reflection or many reflections from the surfaces. And the ray, we call it non-line of sight ray or beam. The angles here in this diagram as shown is phi1 and phi2, which represents the angle of radiation angles, we call them. And the angle here, psi1 and psi2, we call them incident angles. In this figure also, we talk about the sources which we consider Lambertian sources. And a Lambertian source is a source that obeys Lambert's cosine law. And with that radiation intensity in watts per steradian, W, which is watt per SR, which is steradian, the radiation intensity obeys the Lambert's cosine law, which is given by this formula in here. In this formula, we have the parameter phi, which represents the radiating angles, and the M here represents basically we call it the Lambertian order, and it's given by this formula. Phi half, we call it the transmitter semi-angle at half power. Now, the radiant intensity basically is the flux emitted or reflected received per unit solid angle. And it's different from irradiance, where it is the radiant flux power received by the surface per unit area. In the light line of sight visible light communication channel, if we assume that the transmitter emits the radiation pattern in watts per steradian, following this relationship here, PT times R node, and PT is the average power of the transmitted source. Now, at the receiver end, the irradiance which is watt per centimeter square, is given by this formula here, which is related to the radiation transmission divided by D, which is the distance between the transmitter and the receiver in the room. And the receiver power, the received power would be calculated using the this formula here, which is the radiance times A effective, and the A effective is basically given by this formula, which is related to the structure of the receiver, which has a filter, it has a lens, and the filter has a gain, and the lens has a gain, which is given by this formula. It depends on the refractive index of the lens. Now, the receiver structure, it has, as we just briefly mentioned a minute ago, it has a lens, which we called optical concentrator, and it has a filter, and the filter, we have two different configuration on the filter. I'm going to show it to you in a second, and then a detector, which could be a bend detector, and the transimpedance amplifier, which used to amplify the electrical signal detected by the bend detector. The geometry here shows two examples of the receiver front end. One of them here, we have the lens, and the filter is called planar filter, where it's sitting just above the photodetector. Or you may have, for example, hemisphere shape filter, which is placed on the lens, and the detector under the lens. The channel frequency response, typically in visible light communication channels, the frequency response is almost flat near the DC, and that's why the characterization of the Lambertian line of sight channels are given by the DC gain, and using this formula here, which has the terms related to the filter, to the lens, and related to the order, Lambertian order, as well as a detect, which is the detector area. Again, D is the distance between the transmitter and the receiver. Now we replace here, this is the frequency response at 0, because we are talking about the DC gain in this equation. Now, once you apply this equation to the equation which we put before about the radiance and received power, you would be able to characterize the received power of a line of sight channel using this formula here, which depends on the transmitter average power and the other parameters, which is again filter characteristics, the gain of the lens, which depends on the refractive index and the distance, and the area of the receiver. As you see here, we have a condition that the psi, which is the angle, the receiver incident angle, we call it, it has to be less than the field of view angle. If the received angle is more than the field of view angle, then actually you don't receive any power, and the received power would be 0. Okay, now to characterize the channel bit error rate performance, the assumption here, we're going to assume that we have a non-return to 0 modulated signal, and it's on off keying modulation scheme. And using the probability of error, probability of error formula, we're going to have it as a function of the signal to noise ratio using the Q function, which is the Q function is well known given using this formula. Now, signal to noise ratio is the ratio between the signal power and the noise power. So, and the signal power here, we are talking about electrical signal. So we have the responsivity of the detector into the equation, and this is the received power, which we calculated earlier. And in terms of noise power here, we have the we have to account for all types of noises which this LiFi channel would encounter, and we're going to describe them in the next slide. Okay, so the noise sources, the first type of noise sources is the shot noise, which is related to the current produced in the at the receiver, and this is the formula for the shot noise, which is related to the charge of the electrons and responsivity of the detector and the received power, and B is the electrical bandwidth. Now, the other type of noise sources in this LiFi channel is the detector dark current. And in that scenario, it's the noise related to the dark current is almost the same formula here, which is instead of RPR, we have IDC, which is IDC is the dark current parameter. And the other type of noises is we call it background radiation, or we call it the ambient noise, which is related to the noise coming from, for example, the sun if it passes through a window, or any reflection, brightness of the sky or something like that. And the formula for the background radiation is given by this formula here. And the last noise source we consider in this analysis is the thermal noise, which is related to this equation related to the Boltzmann constant, the load resistor, which you basically detect the current with it after transimpedance amplifier. And this formula here, if you add up all these type of noises and plug it into the sigma square total, and you would be able to calculate eventually the bit error rate of the LiFi channel. In here, in this part, we show the component being developed and released in OptiSystem 16.1. We created 3 examples using C++ component, and these examples were used to characterize the LiFi channel, power distribution, frequency response, and impulse response, and bit error rate. And these examples are located in this directory here. I'm going to show it to you. This is under the OptiSystem samples, optical, wireless, and indoor optical link. So this is the examples about power distribution. So how is if you have certain number of LED sources distributed anywhere in the room, and you have a receiver, then this example here shows you how the power distribution of the system would be look like. Now, if you double click on the component here, it's you're going to have a parameters which you can set in the component. You can set up the semi-angle at half power. You can set up the optical power for individual LED. You can set the detector area. You can set the gain of the optical filter, refractive index of the lens, the receiver field of view, and then the dimension of the room, and the distance between, which is the height, d, and the equations which we set before, the distance between the source and the receiver plane. And then we define how many LED arrays and how many LED in each array. So these 2 parameters, one of them defines the number of LED arrays in the like mainly placed on the ceiling, and then this is the number of LED per array, and then the location of these LEDs. So you can control the locations of LED. For more information on this, you can press on the help here, and then you get all the information about the parameters and about some of the way of the setting up the component. Okay. Now, going back into the presentation before I'll do the live demonstration. So this is the component. We have we created 3 C++ component, and at this moment in release 16.1 we created the C++ component to give chance to users to evaluate the models, and if they have any feedback they can get back to us. However, this component, because it's not the final component, you need to download software, free software from GNU-Plot. You can go to this address here on GNU-Plot's website and download the free trial, which you can, once you run the project here, you should be able to see the results. Okay. Now, the other example, the C++ component, the other one is to calculate the channel response, the frequency response, and the impulse response. And in this component, we set up it's almost similar parameters. We set up the field of view for the receiver, the dimension of the room, and then the transmitter mode number, we emitting power of the LED, and the receiver area, and then the number of generated rays. So in this, because we need to calculate the channel response in this component, we need to define how many rays emitted from the transmitter and how many reflection considered. So as we mentioned before, you might have a ray which is line of sight ray going to the receiver, or you might have non-line of sight ray. So you can determine the number of reflection this ray received is gonna go through. And then you have some location of the transmitter position and the receiver position, as well as the number of LED arrays in the array. The last characteristics which for the LiFi channel, which is done also in release 16.1 using the C++ component, is the channel BAR. And in channel BAR, what you need to do is you need to determine the minimum power range and the or signal to noise ratio and the maximum signal to noise ratio. And then with that, you should be able to calculate the bit error rate immediately. Okay, so this is the GNU plot displays for the power distribution. You can see it's a three-dimensional graph which shows you the room dimensions here, and then here the power levels. And this is the two graphs here. It shows you the channel responses, the frequency response as function of frequency, and the time impulse response as function of time. And the last one is give you the bit error rate as function of the signal to noise ratio. Now, what we did in the past few weeks, we developed, we combined the three C++ components, the three models, into a single component using, and the component we call it LiFi channel. This would be released in OptiSystem 17. And this component, basically, I'm gonna show it to you now. Okay, so this is the component which is in release 17 would be ready, and it's placed in the directory on free space optics component. So we have in the free space optics directory and in OptiSystem GUI, we have free space channel component, we have optical wireless channel component, and line of sight channel component, which we're going to demonstrate today also for data transmission. And then we have the LiFi channel, which is again, we combined in this channel. We combined in this channel the three models, which are the, if you see here let me make this is bigger. So you have in this here LiFi channel characteristic, you have power distribution, you can have response, and you have BAR. So it depends on the choice. You're gonna have some parameters, as you see here, it will be grayed, and because you don't need them in that analysis. And if you choose the other ones, you're gonna have other parameters which is available for you to adjust, similar to the C++ component. However, this is one component which is simple to use and it's easy to use. It's a standalone component, by the way, so just only a component which you can use directly once you set up the parameters which you need for the LiFi channel, for the transmitter parameters, for receiver parameters, and for the room which you use. Then you just calculate the component, and then you can look at the graphs using OptiWave graphical user interface graphs. Okay, so move on into the, let me see here, I'm gonna minimize this. Okay. Okay, so now in this part here, we're gonna show you, also demonstrate to you the data transmission over a LiFi channel. So what we did in the first part, we did characterize the LiFi channel, power distribution, frequency response, impulse response, and bit error rate. In this here example, what we do, we use the line of sight channel model in OptiSystem, which is a component ready in 16.0. It's already there. What you need to do in this demonstration, just to show you that you can modulate signal And for example, here we have an LED at wavelength for 50 nanometer, which is a blue LED, and with certain amount of power. And then you can set up the parameters of the LED which you want to investigate. You send a modulated signal and as a non-return to zero. And then what you do here, you transmit over the LiFi channel, then detect it using a band detector. This is the filter we talked about in front of the band detector. Then we have transimpedance amplifier, and then we have a bit error tester. So once you do the design project, you can calculate it. Here we have the setup done at 4 meters of LiFi, the distance between the transmitter and receiver. And in this here graph, we show you later on the bit error rate, which you can achieve based on the setup. As you see in our setup here, we add up a noise, and this noise is representing, for example, the ambient noise which you will encounter in the actual LiFi channel. In the band detector itself, it has its own noise sources, as I'm going to show it to you, where you can set up these noise sources and activate them in the analysis. Okay, so here is a list of references used in the theory and analysis for this component, for LiFi component. Okay, now we're going to go to the live demonstration. So we're going to start with the LiFi channels in release 16.0. So you have, again, we have 3 C++ components. One is the channel power distribution. So if you open this file, and then once you open the C++ component, you set up the parameters, and you have to make sure that your driver path is correct, because if without the driver path correct, you will not be able to run the component. So this has to be loaded properly. And then once you do the calculation, because we have a GNU plot already there, you should be able to see the results. So the results, I have to move them into the other screen here. Okay, so I have. Okay, just give me a second, please. Okay. Okay, so the graph of the results would be shown in this graph here. So this is the not this one. This is the power distribution. This is BER. Okay, so let's run it again. And okay, so the graph is there, but I cannot show them. Okay, so here's the graph, but let me see. Okay, so this is the first graph, which is the power distribution. And the power distribution, as you can see, you can move it 3-dimension and show you the power distribution. Now, in OptiSystem 17, when you have the graph, you will have much better graphical user showing the results. Now, if you look at the second example here, is the channel response. So the same thing, this channel response, if you run it, you should be able to set up the parameters, and then you calculate it's immediately the results will be done. And to show you the results here, this is the frequency response as function of frequency, and this is the impulse response. Okay, and then the last example here, I'm gonna close these ones. Okay, and the last examples here, we're gonna show you the bit error rate. So the bit error rate example, which is in the library under here, and then in this example, same scenario, you can set up the range, the minimum and maximum, and then you do the calculation. And once you do the calculation, you should be able to get the bit error rate curve, which is give you the bit error rate versus signal to noise ratio. Now we set up between 0 to 13 dB signal to noise ratio, and the bit error rate is at each one of those. The other demonstration which I wanted to show you here today is this system, which is a non-return to zero modulated signal for an LED. Now LED here, you can click on it and set up the wavelength, the power level, the lifetime, and all these parameters, slope efficiency. And then you go to the LiFi channel, you set up the distance between the transmitter and receiver, the transmitter half angle at half power, the radiance angle, the incident angle, the detection surface area, optical concentrator factor, index concentrator factor. If you need any help on the theory here, if you just click on the help button, and then you should be able to look at these parameters and the theory behind the component. Once you set up the parameters, for example, here we have the filter, which we mentioned. You can set up the frequency, the bandwidth, the insertion losses, the depth of the filter, and then you go to the detector. Detector here, you set if it is wavelength dependent or constant, the responsivity. You can set up the responsivity. It's here, it's 0.2 ampere per watt. It's very low, but maybe at this wavelength is that amount. We use it usually from practical data sheets. And then here, the dark current, you can include the types of noises which you wanted in the system. So you can check these noises. If you add thermal noise, and if you click on it, you add up the noise, you define the bandwidth, the power density of the noise, and so on. Once you do all of these settings, you also go, for example, the noise, ambient noise source here, determine the noise power spectral density, for example, or the noise power amount. And then here we have the TIE, the transimpedance amplifier setting. So you can set up the transimpedance amplifier. And then eventually, when you do the calculation, I did the calculation before, and this is the results here. Show you the results of this example at 4 meter, as we said. The channel is 4 meter away, the transmitter and receiver, and bit error rate is around 10 minus 16 bit error rate. Now, you can change these parameters, and depends on the system which you're gonna build and simulate. We have a collaborator, actually, we did this kind of simulation experimental and verify the model experimentally. If anyone interested, we can send him the measured and calculated results. Okay, and with this, actually, I'm gonna conclude the presentation, and I'm gonna move into the question period. Okay, so I'm gonna try to answer the questions, and then if you have more questions, you can send them to my email here at ahmed.atiyah@optiwave.com. Okay, so the first question is Lambertian battery source. What it says here. Is written Persian. So I seems that everyone is using the formula with M parameter without explaining the exact origin of this parameter. Do you know where does the generalized? Okay, so mainly if you look at the references, the question is about the formula used for Lambertian source. Like all these references, using this equation, which is Lambert cosine law, to describe the Lambertian source. And in the presentation here, we'll showed you these three references, and you can look at the equations again and how is the theory have been derived in that equations. Okay. Okay, the question here, why we use 1550 in the simulation? So in the simulation, OptiSystem usually defines a reference wavelength, and this reference wavelength is the purpose of it in many components. It identify the parameters at what wavelength is being calculated. So if the component has this, for example, let's say fiber, and you have attenuation, let's say in the fiber, you say 0.2 dB per kilometer, it means that the 0.2 dB per kilometer is specified at 1550 nanometers. Now, some other components, they don't use this reference wavelength. As you see in this component here, we don't use the wavelength. It's just only just to be consistent in the way how we create the graphical user interface. Another question here. It says, when is the release of OptiSystem 17 would happen? OptiSystem 17 the plan is to be before OFC, which is in March. So the plan is to be by end of January, early February of 2020. Okay, another question here says about the modulation schemes used in the OptiSystem, or like, I mean, LiFi channel, what kind of modulation you can use. In principle, you can use any type of modulation. In this example, as you saw here, in this example, we used the non-return to zero. However, you can use whatever modulation scheme in this section and transmit it over the LiFi channel and then evaluate based on that. Okay, so there is a question about integrating MATLAB into the LiFi channel, and OptiSystem has a component in OptiSystem, as you know, or may you know, OptiSystem has in the libraries here something called external software, where you have a MATLAB library, and the MATLAB library you have a MATLAB component, and in the MATLAB component you can write your own MATLAB code and connect this component into your system and allow it to be executed in OptiSystem. And in the component here, what you need to do, you need to define the inputs, number of inputs, number of outputs, and each one of them, what is the signal type, it is optical or electrical or binary or memory, and then you have to use the proper path. And finally, you need to make sure that the signal structure is identified in your code. There is a few examples in OptiSystem about the MATLAB code, how to use it and how to create the simulation as a program as part of the project here. Okay, so this is another question about the modulation here. It says when it will be possible to use coherent techniques in LiFi component style. In principle, as I said again, you can choose your concept here, the modulation scheme which you like, and that the receiver end has to be matching or working with the transmitter modulation scheme at the transmitter. If you do that, it should be this is like the LiFi channel, which should be similar to any medium of transmission which you use, like for example in optical fiber. You can think about it as exactly the same concept. Okay, so with this, I'm gonna actually end this session. The remainder of the questions, we look at them and then we're gonna email them to the users. Thanks you very much for listening and attending this webinar.
All right, thank you for tuning into this live webinar. We'll be emailing the link of the webinar recording to everyone at noon tomorrow, Eastern Standard Time. Sorry, actually we'll be emailing it an hour after the presentation. And we had a lot of questions in this webinar, so any questions submitted during the webinar that we haven't had a chance to answer will be answered via email. We also encourage anyone with more questions about the software or anything from this presentation to email us at support@optiwave.com. We appreciate you attending this webinar, and have a good day.